So for section 7.7, we're just going to do some applications of the rational expressions. So a couple word questions, but mostly I want to focus on kind of the work questions and mixture questions. If some number is added to both the numerator and denominator of the fraction 3/4. Okay, so I'm taking the fraction 3/4 and I'm adding something to the numerator and the denominator. Okay, so I'm taking 3/4 and I'm adding something to the numerator and denominator, and the result is 3 greater than that number. So that number plus 3. Okay, so in this situation, what we're looking at is, once again, we have rational, we have a fraction. We can clear it by multiplying by our LCD, which happens to be the 4 plus x. If you want to make that x plus 4, that doesn't hurt my feelings. But at this point, I already have 4 plus x, so I think I'll just stick with it. If I do it to one side, I have to do it to the other. Alright, so what happens here? Well, on the left, the 4 plus x cancels with the 4 plus x. That's a good deal. On the right side, 4x, x squared, 12, and 3x. So I'm recognizing right now that this, once again, is an ax squared plus bx plus c. So I want that equal to 0. So I'm going to go ahead and, while I'm combining the like terms, I'm going to move over the 3 and the x. So I'm going to move over the 3 and the x so that the left side zeroes out. And the right side, let's see, we've got 3x plus 3x. Oh, first of all, bring down the x squared. Plus, that should be 6x plus 9. We want to factor this. So x and x, 3 and 3, both positive. And then to solve it, each group set equal to 0. Since they're the same group, I don't need to do that twice. But we end up getting x equals negative 3. Okay? And I can actually check that. So just to make sure we're not totally crazy here, where do we go up here to the original? I can do 3 plus negative 3 over 4 plus negative 3 should be equal to 3 plus negative 3. We got 0 divided by 1 is equal to 0. 0 equals 0. This is true. So that is our answer. Next I want to talk about just dirt. This is the way I've heard it referred to in the past. Distance equals rate times time. We do this naturally, and I want to just take a second. If we had a person who was running, let's go ahead and say 5 miles per hour. Okay? And they ran that for 2 hours. Well, what would the distance be that they traveled? Well, you would just do 5 times 2 and go, well, yeah, that's 10 miles. We do that naturally. I go, well, what if they were real ambitious and they were able to hold that for 3 hours? Well, then they'd go 15 miles, right? What are we doing? We just take the rate times the time to give us distance. We do it naturally, right? But this is just a formal formula that we refer to as distance equals rate times time, or dirt. I have had students say if you take the equal sign, you could even like cross it and make it look like an I in dirt. Just something. So this is the one that you need to know. Sometimes we will be doing different things with like different rates. So I could take this equation and I could solve for rate by dividing both sides by time, so that rate is equal to distance over time. I don't have to have that one memorized. All I need to know is the first one, and I could come up with another one. Same thing if they give me distance, rate, and time, and they want me to solve for time. Well, I would divide both sides by the rate and get that time is equal to distance divided by the rate. So once again, I don't need to memorize all of these equations. You do need to know the top one, and then we could derive the other ones. How are we going to apply this? Well, here's a question about rates. Amy and John leave Waco, Texas, at the same time driving north on the I-35. Amy drives twice as fast as John, and in 3 hours, she is 105 miles ahead of him. How fast are they driving? Well, what is John's rate? Well, we don't know, right? I always like to say, find the comparing words. We are comparing Amy's rate to John's rate. So I would call John's rate, because John's rate is what we're comparing to, as John's rate, I would call his rate X. Because then I can say, well, Amy drives twice as fast, so her rate would be 2x, twice as fast. Okay? You don't necessarily have to do this on this question, but I do suggest something we could do is actually set up this table for distance, rate, and time. If you've had this class before, you've had Math 55, you've just seen this in there. But I take distance equals rate times time, and I basically can fill in distance, rate, and time for John and Amy. Okay? So, let's see. Rate for John we just called X. Rate for Amy we called 2X. They drove for 3 hours. They were the same, so their rate would, or their time would be, okay? And then we have John's distance, and we have Amy's distance, okay? So John's distance, and we have Amy's distance. And we don't know either of those, right? But from this I can say that John's distance is equal to X times 3. Or John's distance is equal to 3x. From this, I can say Amy's distance is equal to 2x times 3, or Amy's distance is equal to 6x. So how do we solve this now? Well, there's this 105 miles ahead, so basically we can make that into one more equation and relate them all. Here's the idea. They both leave from Waco, and they head the same direction. John, after 3 hours, is right here. This is John's distance. Well, Amy got further, didn't we? She left from Waco as well, and she got John's distance plus another 135 miles. So we can basically say, well, Amy's distance is equal to John's distance plus another 135 miles. Well, I don't really want two variables, but we can replace them, because Amy's distance is 6x. So 6x is equal to John's distance is 3x. So 3x plus 135. I can now solve for x and say, looks like 3x is equal to 135. If I divide by the 3, we get that x is equal to, I believe it's 45. Is that what they asked? They asked for the rates, right? So John's rate was x, was 45. Amy's rate was twice as much, which was 90. Excuse me. Here's another way of handling a different type of rate if you're dealing with combining work, combining people's rates. Instead of, it's still kind of a version of DIRT, D equals rate times time, but we're measuring jobs. So just like you can do distance over time, you could do jobs over time. So that could be like painting a room. How many rooms can you paint over how much time it takes? It could be typing a paper. How many words per minute? Job over time. So how do we get that job over time? Well, it's easy. Instead of DIRT, because we're not measuring distance, we're now measuring jobs. You get JIRT. Nobody calls it JIRT. But the idea is what? Jobs will still equal rate times time. I can solve for that rate by dividing by time. And so the rate will be the number of jobs that get done divided by how much time it takes. For all the questions you're going to see, they're going to be dealing with one job. So that's nice. That means there's a 1 up here. Okay? And then we'll have the time is going to be kind of their individual time. If I'm combining rates, then what I can do is I can take the first person's rate times time, go 1 divided by the first person's time it takes them, plus 1 over the time it takes for person 2. These are basically the two different rates, and we can combine those rates, multiply them by a common time, and figure out how long it takes to take one job. There are other ways of kind of explaining this, but I found that this is kind of the most successful, quickest way of getting the answer. So I'll kind of show you how this works with an example. We're going to take 1 divided by the time it takes for person 1, 1 divided by the time it takes for person 2, multiply those by a common time, and figure out how long it takes to get one job done. The Gumans need to mow their lawn before the guests arrive. With the riding mower, Sarah can mow the lawn in 30 minutes. We could figure out Sarah's rate. Sarah's rate is one job, one lawn mowed in 30 minutes. With the push mower, Sam can get the job done in 1 hour. That's a second rate. Sam's rate is that he or she, whatever, gets one job done in 1 hour. I need a common amount here, so I'll put 60 minutes. Okay. What if they're working together? Well, one thing to keep in mind, this always irritates me. If it takes one person 30 minutes and the other one 60 minutes, I'll have some people just go, I don't know, just average them, 45 minutes. That's utter nonsense. If it takes one person 30 minutes and working together it takes them 45, one of those people is completely unnecessary. It should take less than 30 minutes. If Sarah can do it in 30 minutes by herself, even with Sam working twice as slow, it should save her some time. Okay? So what do we do here? We don't know how long it takes for them to work together, but we could combine their rates. Sarah's rate, 1 over 30 times time, plus Sam's rate, 1 over 60 times time, and we want to figure out when will that equal one lawn mowed. If I wanted 2 or 3 lawns, then I would just change this number at the end. They're going to keep it as a 1 in your homework. So how do I solve this? Well, you clear the fractions. We multiply by our least common denominator for 30 and 60. So that means that 60 is going to go across each term. 60 divided by 30 is 2t. 60 divided by 60 is 1t. And 60 times 1 is 60. Now it becomes very easy to solve for t. 3t is equal to 60, so that t is equal to 20. So with Sam helping with that push mower, it saves 10 minutes. We get the lawn mowed 10 minutes faster. Okay? And really, it saves Sam 40 minutes, so that's kind of a good deal for Sam. When will you ever use this? You're not necessarily sure at this point. I don't know what you're going to do with this, but I do want to tell you that I always love to bring up in this situation. I have a brother who never knew when he might use this. He's not like a mathematician. He's a painter. And so he uses this all the time. He has people that work for him, and he knows how long it should take them to do one room. And he knows how long it should take 2 people. And if he puts 2 people in there, and they take longer than they should, somebody's not necessary. Somebody needs to be let go. Somebody needs some time off, and maybe, come back when you're ready to work. So this is kind of an important thing that he uses all the time. He's not pulling out a pen and paper, but he's figuring out these types of things. Let me give you an example of that. So Richard can paint a room in 2 hours. John can paint it in 3 hours. What if they are working together? Well, Richard's rate would be 1 job in 2 hours. John's rate would be 1 job in 3 hours. So combining Richard's rate times a common time, John's rate times a common time, how long should it take them to do 1 job? Clearing out the fractions, least common denominator of 6, we have 3t, 2t, 6, 5t equals 6, and t equals 1.2. So working together, it should take what? 1 hour, 12 minutes. If it takes them an hour and a half, somebody's slacking. If it takes them 2 hours, then somebody shouldn't have even been there. Richard could have done it in 2 hours by himself. If it takes him an hour 15, yeah, probably don't freak out about that. If it takes them an hour, maybe one of them gets a raise, right? Maybe you give them a bonus. So you want to encourage, but you should have an overall calculation of how long it should take 2 people working together. Okay? So that's it for this section. Get ready for the test, and see you guys soon.